Hello, and welcome to Controllers Tech. As promised in the previous video, today I brought to you another video on the GPS module, where we will interface the module with the STM32 microcontroller. As many of you might be using the Neo GPS modules, I have also switched to Neo 6M for this video, but it does not matter, as I have mentioned before, the output from all the GPS modules is pretty much the same. They all outputs the data in the NMEA format, and that is why you can use this method for pretty much every GPS module out there. If you remember from my previous video, this is the output of the GPS module in the NMEA format. Before starting this video, I would want you guys to get familiar with the ring buffer code. If you got the ring buffer code to work, you can go ahead with this one, or else first try to make that work. Like I said, I have switched to Neo 6M, and I have connected it with the STM32 UART to TTL device. You can see the connection. The LED on the 6M is blinking, this means that we have the fix on the signal. The TX pin from the 6M is connected to the RX pin of the FT232. It's also connected to the RX pin of the UART1 of the blue pill. But for now let's focus on the FT232. The module is powered with 5 volts, supply from the blue pill. You can see the data it is transmitting via the UART. It's basically the same format as the previous GPS module. Now I am going to connect the module to 3.3 volts supply, and we will see the UART output. You can see the output. If you are getting something like this, make sure you provide proper voltage supply to the module. Here I have switched back to 5 volts, and the transmission begins again. Let's keep these things in mind, and create a new STM32 project. I am going to use STM32F103 controller for this. Give some name to the project, and click Finish. Enable the external high-speed crystal for the clock. Also we need to enable the serial wire debug. There is 8 MHz crystal on board, and let's run the system at maximum 72 MHz clock. Alright, now we will enable the UART. Since the data incoming is of uncertain length, we need to use some circular or ring buffer for the UART. I already did a video on it few years ago, and if you have made it work, you are good to go with this tutorial also. I would recommend that you watch that video first, if you haven't did it yet, as this code will heavily depend on that video. Let's enable the UART interrupt now. Neo 6M works with 9600 board by default. I am relocating the UART pins for my convenience. PB7 is the RX pin, and PB6 is the TX pin. This is it, click Save to generate the project. This here is the ring buffer code that I am going to use. Here are the steps provided for this particular code to work. I have already downloaded the ring buffer files, and now we will copy them into the project, along with the NMEA files I have created specifically for this tutorial. put the C files into the source directory, and header files into the include directory. Let's see the ring buffer.c file. We need to put this in the interrupt file. First include the UART ring buffer header file. Now define the UARTISR function as extern. We need to also define the timeout as external variable. This is needed for the timeout feature to work. Inside the SysTick interrupt handler, decrease the timeout value. Finally, inside the UART interrupt handler, replace the interrupt handler with UARTISR function. Make sure you update the correct UART instance you are using. I have modified the RX buffer size to 512 bytes, as there is large data in the incoming buffer. Other than this, the ring buffer code is pretty much untouched. Let's include the UART ring buffer header file. Also include the NME header file in the main file. This is how the NME header file looks like. Note that it only have two functions, to decode GGA and RMC. If you have watched my previous video on GPS, you will know what these terms means. These two gives enough information for now. Alright, let's initialize the ring buffer now, and build the code to check for any errors. There are no errors, we can go ahead. Let's debug the code once. This is to make sure if we are receiving the data in the RX buffer or not. Let's add the RX buffer to the live expression. Run the code now. Let's see the buffer itself. Here you can see we got the RMC string, or if you get any other string also, it's alright. The main thing that we are checking is if we are able to receive data or not. Alright, so the RX buffer is receiving data, and we are good to go. Let's define an array to store the GGA data, and another one for the RMC data. Next we will define this GPS structure in the main file. Actually the decode functions take respective structures as the parameters, but GPS structure contains both of them, and therefore we will only define it. Give some delay after initializing the ring buffer. Now we will wait for the GGA string in the incoming buffer. If the string is detected, the function will return 1. This function also includes the timeout feature, just in case if the string is not detected, it will time out, and the execution will continue to the next statement. If the string is detected in the incoming buffer, we will copy up to the star mark, and we will save this data in the GGA buffer we created earlier. So basically it will wait for this GGA, and once found, it will copy up to this star mark. This entire data in the middle will be saved in our GGA buffer, which we will process later. After copying the data, we will call the decode GGA function. The first parameter is the GGA buffer, where the data was saved. And the second parameter is the GGA structure. Here we will pass the address of the GGA struct element of the GPS structure. Let's build the code to check for any errors. Alright, we are good to go, so let's debug this much part first. Add the GPS data in the live expression. GGA structure have location, time, altitude, and the number of satellites. It also have the means to check if the fix is valid or not. We have time here, then the coordinates. This one indicates that the fix is valid. 4 is the number of satellites. This is the altitude. Alright, let's run the code. We got the hard fault. Let's put a breakpoint inside the wait for function, and run it 2-3 times. Now remove the breakpoint and let it run freely. Here you can see is fix valid is set to 1. And if you see the coordinates, they are pretty much accurate. Time is also correct. For the time conversion, I have included this variable, and you need to edit it in the code. The time part is still needs to be tested, so if you are getting wrong time, let me know in the comments. So everything is working well, and we were able to decode the GGA parameter from the NMEA data. Let's write the same code for the RMC parameter also. This needs to be decode RMC. Alright, let's debug the code. You can see all the parameters are pretty much working fine. The date today is 28th February. Things are working fine, and the GPS data we are getting is also accurate. Let me explain the code, so that you guys can decode other things also. Let's see the decoding of the GGA. We first skip 6 commas. If you check the collected data, you can see this one comes after the 6 commas. We look at the data at this position. If the value is 1, 2 or 6, that means the fix is valid. For any other value, the fix will be invalid, and we will return with some error code. By the way, this function returns 0 on success, and other numbers based on where the error returned. If the fix is valid, we will continue with the decoding, and first of all we will copy the data between first and second commas. This data represents the time in UTC. Next step would be to extract the time, and adjust it according to the offset. This part is still untested, and if you get any error in time, let me know in the comments. Next task is to get the latitude. Since we have already hit the comma in the previous copying, we will increment the index to reach the first digit of the latitude. Basically here. Now we will copy this entire data into our buffer. After copying this data, we will convert the string into the number, and do the necessary calculation to extract the latitudes from the data. We will increment the index again, and check for the north or south parameter. Similarly, we will get the longitude data, convert it into the number, and extract the longitudes from it. Next we will skip the position fix checking, since we already checked it, and directly calculate the number of satellites being used. And finally get the altitude data, and convert it to number format. Similarly we can decode the RMC data, and extract the date, speed, and other things from it. I will comment this code before uploading it, so that you can understand it better. Now I know there will be some of you who will still ask about how to display it on the LCD. So I have decided to include that part in the video itself. I am going to use the I2C to connect with the LCD1602. This is why I have enabled the I2C one. Everything is set to default here. You need to include the I2C LCD libraries in the project. Now in the main file, if the GGA string is detected, we will set the Vcc timeout to 5000. This Vcc timeout is basically for checking if we are receiving the data or not. You need to define it externally in the interrupt file, just like we did for the timeout. Also similar to timeout, we need to decrease its counter in the SysTick interrupt handler. This is where it's defined. Also note that I have defined the flags for the GGA and RMC. These flags will be set if we receive the valid data from the GPS module. Also there is a LCD buffer, which will contain the character data, respective to numerical values. Alright, after the GGA string is detected, we will reset the VCC timeout, and copy the GGA data into the buffer. If the decoding results in a success, we will set the GGA flag to 2, or else set it to 1, indicating that the string was received, but the fix is still invalid. Similar steps for the RMC data also. Now if either of the received data is valid, we will put the LCD cursor to 00. Then use sprintf to convert the numerical data into the characters, and save it in the LCD buffer. The first half of this will be hours, minutes, and seconds from the GGA structure. And the later half will be the date from the RMC structure. Once the converted data is saved into the LCD buffer, we will send it to the LCD. Then reset the buffer, set the cursor to the second row, and convert the location data. This .2f is to convert the float data in 2 decimal places, which is basically the latitude. The C here indicates the character, which indicates whether it's north or south. Similarly we have for the longitude, and the character for east or west. Finally we will send this data to the LCD. Now if the either of the flags is 1, indicating that the string was received, but the fix was invalid, we will print the respective information on the display. Notice here that I am not clearing the display, but instead I choose to go with the spaces. This is to ensure that every time we are waiting for the fix, the screen shouldn't feel like it's refreshing. Finally, if the VCC timeout is 0, that means the GGA or RMC strings were not detected in the incoming buffer. This could only mean that either the voltage is insufficient, or there is some problem with the connection between the module and the microcontroller. So here we will print the respective information on the display again. Here you can see I have taken some pictures for each case. This is when I provided 3.3 volts to the module. This is when the voltage was fine, but the fix was invalid. And this is when everything was alright. So this is it for the video. I hope you understood the concept well. Decoding the NMEA could be better, and I know there are some libraries available to just parse this data, but I like to use my own code for whatever I can, and that's the only reason I wrote this. If you are getting errors in the ring buffer library, better comment below the ring buffer video, instead of this one. You can download the code from the link in the description. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.